welcome back. So, in today's lecture, we are going to continue to look at drug metabolism. So, we discussed previously that once a drug enters the body, it is going to be exposed to a number of enzymes, and these enzymes are going to act on it, and they can do a variety of reactions. We looked at a list of reactions last time, and how these reactions are going to mainly convert the drug into something that is more water soluble, so that it can be excreted through the kidneys, or it can be excreted through the bile. So, now let us continue to discuss these topics. So, now let us recap some of the main things that we have discussed in the past couple of lectures. So, basically we looked at the concept of ADME, which is basically absorption, distribution, metabolism and excretion. And we also saw that there are two phases of metabolism, and both these processes typically end up making the molecule more water soluble, so that they can be excreted. And we introduced this enzyme known as the super family of enzymes known as cytochromes P450, which are pretty much non-specific enzymes which can carry out these metabolic reactions. So, many of the phase 1 transformations are catalyzed by flavin containing monooxygenases. So, this is another important group of metabolic enzymes present in the endoplasmic reticulum of the liver cells. Okay? And these monooxygenases, as the name suggests, is going to end up taking one oxygen and putting it in a molecule, and these are chiefly responsible for many of the oxidation reactions. Okay? And the targets of these oxidations are nucleophilic nitrogen, sulfur and phosphorus. Okay? And they prefer these atoms over carbon atoms. So, here is the structure of flavin. So, flavin is basically a highly delocalized structure, and it is commonly known as vitamin B2, which is riboflavin, and riboflavin is enzymatically converted into two forms. So, let us look at both these forms now. So, one is called the flavin mononucleotide, whose structure is shown here, and the other one is flavin adenine dinucleotide, which is FAD. Both these are functionally equivalent, but some enzymes use FMN and some enzymes prefer to use FAD. Okay. So, it's this molecule contains a highly conjugated isoalloxazine tricyclic system. So, here is the tricyclic system. Right. And it has very strong redox properties. We will look at these very shortly, and they can accept either one electron at a time, or they can accept two electrons simultaneously. Okay. And in many overall 2 electron oxidations, it is sometimes not clear if the reaction proceeds by 2 1 electron processes or by 1 2 electron process. Okay. So, now let us look at some of the aspects of how this flavin works. So, here I am going to draw the structure of flavin on the left. So, basically the tricyclic system is as follows. It has a benzene ring, and it has a nitrogen, right, and the third cyclic system is here, which has a C double bond O, nitrogen, C double bond O, and this structure has 2 nitrogens in the center, and this is the methyl group CH3, and since it is a highly conjugated system, you can imagine there is a double bond here, and an NH over here. Okay. This is called flavin oxidized form, or FLOX. So, this group here is R. So, this is the main portion of the flavin molecule, which contains 3 rings, and it has a number of functional groups. It has a conjugated system, right, and once it picks up one electron, right, it can assume a similar structure, which I am going to draw here. So, the benzene ring here remains the same, and the nitrogen over here picks up 1 electron. This nitrogen remains the same, and you have O minus here, NH here, C double bond O. This nitrogen remains the same, this nitrogen remains the same. So, this intermediate has a 1 electron here, as you can see, and this is called as Fl dot minus. Okay. So, what happens in this process is that the flavine ring picks up 1 electron, and it just results in a rearrangement of electrons to produce a nitrogen base radical and a enolate. Now, this molecule can further pick up 1 more electron, which we will look at now. Okay. So, this will pick up 1 more electron, and which I am going to draw over here, and these are reversible processes. So, you have a benzene ring which remains the same. The second nitrogen is the one where the electron is going to be transferred, and you have the C double bond O N, C double bond O N. This becomes a negative charge, and the double bond is moved over here, and this becomes NH. Okay. So, what ends up happening is that this electron actually communicates here with this ring and picks up the electron and produces a full negative charge on this nitrogen on top. Okay. So, this species is called FlH minus, right. So, these are the 3 main species that are involved in the flavine redox process. Now, it is also possible that you can convert this to this by adding 2 electrons, and you can do the reverse process by subtracting or removing 2 electrons. So, this is how the entire flavine redox process occurs, and this is called the semi-quinone form, okay, and this is the fully reduced form, which is FlH minus. Now, although most flavine dependent enzymes bind the flavine in a non-covalent manner, some of the enzymes actually bind to it in a covalent way, right. So, this covalent bond happens at this 8 alpha position or at the 6 position. Okay. So, we will not go into too many details, but we will look at one example later where this kind of a bond occurs. And the residue that binds to this is either a histidine or a cysteine. So, once the flavine has been reduced, now the enzyme requires a second substrate to return the flavine to the oxidized form, so that it can accept electrons from another substrate molecule. So, some flavoenzymes are called as oxidases, and others are called as dehydrogenases. Okay. The distinction between these names refers to the way in which the reduced form of the coenzyme is reoxidized, okay, so that the catalytic cycle can continue. And keep in mind that we looked at the entire the 3 redox forms of flavine, and this is a reversible process, and so flavine can get oxidized as well as reduced. And so, the mechanism by which this occurs is what we are going to look at in very briefly in the next few minutes. But depending on how it is it goes back to the oxidized form, it is called an oxidase or a dehydrogenase. So, the enzyme that utilize the electron transfer protein, such as the first class of enzymes that we are going to look at are dehydrogenases, and these enzymes utilize electron transfer proteins such as ubiquinone or cytochrome B5 to accept electrons from the reduced flavine. So, let us now draw the structure of reduced flavine very quickly. And so, here are the 2 methyl groups, and here is the central ring, and here is the third ring of flavine. So, there are 2 nitrogens here, the nitrogen is here, nitrogen here, C double bond O, C double bond O, and you have N minus, NH, and we have R. Okay. So, what happens is that you can push 2 electrons in here, and this is actually going to donate a single electron. Okay. So, when we are looking at a single electron, we always draw a fish hook arrow, and this is going to be donated to some acceptor molecule, and the second species that is going to be produced is N. So, if you draw the arrows, you have a double bond over here with N, and then there is C double bond O, N, C double bond O, and this carbon actually ends up with a radical. The rest of the molecule is the same, and there is an NH popping out here. And now, you can imagine that there could be a base from a protein, which then picks up this hydrogen and it transfers 2 electrons over here, and this is in turn given back by a 1 electron process to the acceptor dot minus. Okay. So, now the acceptor, which is in the form of a radical anion, becomes acceptor negative charge, and you get back the oxidized flavin, whose structure I am not going to draw. Okay. So, this is the process by which 2 1 electron transfer can occur, and this is the mechanism by which dehydrogenases act. Oxidases, on the other hand, use molecular oxygen to oxidize the coenzyme with the concomitant formation of hydrogen peroxide. Now, let us look at the way in which oxidases are going to function, and one of the ways in which this can happen is by reaction with triplet oxygen, which leads to the formation of a cage diradical pair of superoxide by electron transfer, and then superoxide after spin inversion can undergo either radical combination or second electron transfer from flavine semiquinone to go directly to the oxidized flavine. Okay. So, again we will not look at too many details of this mechanism, but at the end of it you will end up producing hydrogen peroxide. So, if we were to look only at the central flavine ring, you have NR, NH, this is the same species which is N minus over here, C double bond O, NH, then this double bond O, rest of the molecule remains the same, and you have a reaction with O dot dot, and this produces, the arrow pushing is pretty much the same. You have a fish hook arrow, this O attacks here as again a fish hook arrow, and you end up producing a radical intermediate such as this O dot, C double bond O, NH, double bond O, N, and now this forms a double bond, rest of the molecule remains the same, right, and then this can subsequently get oxidized and produced H2O2 and regenerate the flavine. Okay. The analogous reaction with singlet oxygen to give the flavine hydroperoxide directly is also possible, and it will occur only if there is a mechanism of spin inversion from the normal triplet oxygen, because normally triplet oxygen is what exists, and so this singlet oxygen is produced in situations where there is a metal ion, and again there is loss of hydrogen peroxide to give the oxidized flavin. So, we will not look into the details of this mechanism, but this is another way in which you can regenerate flavin after the redox reaction. Okay. Now, there are a number of reactions that are catalyzed by flavin dependent enzymes. Let us look at some of these. So, the first example that we are going to look at is RCOH, which is an alcohol going to a ketone. Okay. You can also have amines getting oxidized, such as this NH2 R prime, giving you R C double bond NH, which is an amine, which is going to be an intermediate, which will then subsequently form R C double bond O R, which is a ketone, plus NH4 plus. Okay. The third reaction that can happen is an oxidation reaction of to produce an olefin, So, here you have the example that we are going to look at is CR prime C H H R double prime to give you, and this carbon carbon bond is going to form a double bond, and you end up with this ketone. Okay. So, this is again an oxidation reaction that is catalyzed by flavin dependent enzymes. The next class of reactions is the formation of a disulfide bond. So, you can have R C S H, you can have a long chain maybe with another SH over here, okay, and this can undergo oxidation to produce a disulfide linkage such as this. Okay. So, this is the next one possible. Flavin dependent enzymes also can oxidize benzene rings to give you the corresponding phenols. We have already looked at this in the previous lecture, and also the oxidation of phenols to catechol is also possible. Okay. So, these are the major reactions that flavin dependent enzymes can catalyze, and as you can see, all of these are metabolically very important, and therefore, flavin dependent enzymes become a very important class of enzymes that are involved in drug metabolism. Lastly, they also can oxidize carbonyl compounds such as R C double bond O R. So, this is a ketone to form a ester. Okay. So, this ester formation is also possible. You can also form an ester from an aldehyde by flavin dependent monooxygenases. So, you form a carboxylic acid from an aldehyde, and lastly you can also have the oxidation of hydroxy acids to produce COOH, which is basically this part of the molecule is going to get oxidized and the other part of the molecule is going to form carbon dioxide. So, all of these are catalyzed by flavin dependent enzymes. There are 4 types of mechanisms that can be considered, which involves a carbanionic intermediate, and then one with a carbanion and a radical intermediate, and one with a radical intermediate alone, and the last one is only with a hydride intermediate. So, these have been studied extensively, but no definitive mechanism is possible, is known. Some of these may be applicable to different flavor enzymes, and also it also depends on the substrate. So, the principles of these mechanisms remain pretty much along these lines, but the exact definitive mechanism is difficult to ascertain. So, now let us look very quickly at the 2 electron carbanion mechanism. So, here the example that we are going to look at is D-amino acid oxidase. So, let us draw out an amino acid. So, basically it is NH3 plus COOH, and this is the hydrogen, and the final product that you are going to get is a keto acid, which is basically R C double bond O COOH. So, the first step in this mechanism is a flavin dependent reaction. So, let us look at that reaction. So, if you draw out the nitrogen ring of flavin, as shown here, and you have the molecule looks like this. Here is the flavin ring. So, you have N double bond N and another N double bond N. So, you can imagine that there would be a base that would come abstract this hydrogen, and this can then be transferred to C minus, and that will give you R C minus NH3 plus COOH. And since this carbanion is next to a electron withdrawing ammonium ion as well as a carboxylic acid, it is possible that it can be stabilized to some extent, and then this carbanion can then react over here and give you this stable N minus, and so the intermediary species that you would be producing would be N C COOH NH2 R, and the rest of the flavine molecule is as we would have drawn it out previously, right. Okay. So, now for to this species you would need the base which is here B H plus, which has picked up a proton from here, and this nitrogen would probably push in the electrons over here, and this goes and picks up a proton and regenerates the base. So, you end up with a product that is C double bond N COOH R, right, which then undergoes hydrolysis to give you the ketone. Okay. So, this is the 2 electron mechanism in a nutshell. There are many standard books wherein you can obtain this mechanism. Okay. So, the another 1 electron mediated oxidation reaction is an enzyme called as monoamine oxidase. This enzyme is a really important flavor enzyme in medicinal chemistry. It is one of the enzymes responsible for the catabolism of very important neurotransmitters such as norepinephrine and dopamine. So, these are the structures of norepinephrine and dopamine, and they are oxidized to the corresponding aldehydes. Okay. And monoamine oxidase exists in 2 isomeric forms, MAOA and MAOB, and they catalyze this reaction which wherein the norepinephrine or dopamine is converted to the corresponding aldehyde. Now, we will look at mechanism of heme dependent oxidation reactions. So, heme is a very important part of, we looked at previously cytochrome P450, they are heme containing proteins, and it is useful to carry out many oxidation reactions, and of course, this process is dependent on flavin as a cofactor. Okay. So, the reaction of heme dependent oxidation involves a Fe double bond O species, okay, and this species is formed from heme, and that process is mediated by flavin. So, if we were to look at the structure of heme in a very simplistic manner, basically it is a porphyrin ring with iron in the center, right, and you have many ligands on the top. So, this oxidation reaction is catalyzed by flavo enzymes to give you Fe double bond O nitrogen, 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 right, and this is now involved in, is the major species that is involved in oxidation. So, let us look at this species again. So, you have Fe double bond O with the porphyrin ring over here. Again, as I mentioned, this species is obtained from heme by flavin dependent enzymes. So, now if you have alkane, for example, R prime, R double prime, this reacts with the heme oxidized Fe double bond O with a radical mechanism. So, you have a radical that is produced over here, and this first is picked up, one of the electrons goes here and the second electron goes here, and this carbon hydrogen bond undergoes reaction again to produce a carbon centered radical. Okay. So, we will produce FeOH, right, and now the oxidation state of iron here is +4, the nitrogen, 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 and the product that is formed is C, R, 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 which is basically a radical, and now you can, there is an oxygen that is going to be transferred over here. The second bond breaks, this is the bond that is formed, and then this is going to go back into the ion system, and you get Fe3, right. And of course, in this all this there is a cysteine residue that is bound to the ion. Right, and you get OH, C, R, R, R. Okay. So, this is the general principle by which heme dependent enzymes work. So, in the first step, you have the formation of a iron oxo species, which has a cation radical on it, which then is able to involve itself in radical reactions with an alkane, for example. We end up with a carbon base radical, which then reacts further with a OH dot that is transiently produced to give you the alcohol and gives you an Fe3 complex. Okay. Using the same principle, the epoxidation reaction also occurs. So, again we should look at just the key steps of this mechanism. You have Fe double bond O, you have the nitrogen, 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 nitrogen. Okay. And as I mentioned earlier, there is a cysteine residue over here, which is going to anchor itself to the ion, and you have an olefin R, R, and as I mentioned, there is a radical cation over here. So, you have the formation of a radical species, here is formation of another radical species, and this is now donated over here. The second electron is given to the radical cation of the nitrogen and end up with Fe O carbon, R, H, carbon, R, radical, H, rest of the molecule is the same. Iron is still in oxidation state 4, continues to remain in oxidation state 4, and you have a thiol residue that is attached here. And once this is formed, now there can be a reaction of this radical with oxygen in the following manner. This donates one electron, this donates the other electron, and then this goes back here to give you Fe3 porphyrin with the sulfur remaining here, and the product is the epoxide. Okay. So, this is broadly speaking the mechanism by which epoxidation occurs. In a very similar manner, you can also have heteroatom oxidations such as R, S, R going to R, S double bond O, R. Okay. So, I am not again going to go into the details of the mechanism, but you can imagine that there is going to be a radical that is formed on the sulfur because of one, you have a lone pair on sulfur, which can donate one electron, and then once that radical is produced, it again forms a bond with oxygen to produce a Fe O S type of intermediate, which then rearranges and gives you the product. Okay. So, these are all examples of oxidative phase 1 reactions, but there are also several reductive phase 1 reactions, but they are less common, and the main reductions that occur are of aldehyde, ketone, azo and nitro functional groups. So, let us look at some of these examples very briefly. So, you have an aldehyde which is going to give you RCH2OH. Similarly, you have a ketone which will give you a secondary alcohol. Okay. And you can also have an alpha beta unsaturated compound such as a Michael acceptor, which can and give you R over here. So, that is the hydrogen has been added over here. You can also have alkyl halides giving you RH. So, all these are formally reduction reactions and they can all occur in reductive phase 1 reactions, but they are less common. As I mentioned earlier, you can also have nitrogen based compounds undergoing reduction. So, you can have N oxides, which we looked at previously, going to R N R R, and these are typically methyl groups that are happening, that are quite common. You also have nitro groups which can go all the way to RNH2. Okay. You can also have azo compounds such as these, giving you R N N H R. So, all these are reduction reactions, and this can further undergo reduction to give you 2 moles of RNH2. Okay. And these R groups can actually be aromatic rings as well, and those are going to give you the corresponding aromatic amines. Of course, we know that disulfides are very common. Disulfides can also be reduced to form 2 moles of thiols, and sulfoxides, which are S double bond O, can also be reduced to form R. So, again these are all possible, but they are all less common compared to oxidative reactions.